Okay, guys, so I'm going to be looking at some CXC questions here that may be taken from different papers. And these are numbered from 38 to 60. So let's go. All right, this one says a ray of red light enters a semicircular glass block normal to the curved surface. Which diagram correctly shows the partial reflection and refraction of the ray? All right, so in a question like this, one has to be very careful. You need to know that the angle of incidence and the angle of reflection should be equal. So if we draw, what you can do is to just estimate where a normal would be at this boundary. So we're going to put in a line, roughly. I'm going to get it straight here. We'll put a line at these points just to have an idea of the angles here. Now we can clearly see that in A, the angles are not going to be equal, neither in B. In C, they are appearing to be roughly equal. But when the ray is coming from the glass into the ear, it should bend away from the normal. The red lines here we use as the normal. So in this case, the ray is not bending away from the normal, but towards the normal in comparison to where the ray would have gone if it wasn't refracted. In D, we see that the ray is bending away from the normal. So I'll choose D for this one. All right, so we have angle of incidence here, angle of reflection here, roughly equal based on our estimation. And we have the refracted ray bending away from the normal. Question 39 says an object 5.0 centimeters high is placed 2.0 centimeters from a converging lens, which is the same as a convex lens, which is being used as a magnifying glass. The image produced is 6.0 centimeters from the lens and is 15 centimeters high. Here to find out the focal length of the lens. So we can use the lens formula here. And one version of the lens formula is F is equal to V times U. We have V times U over V plus U. It's the simplest way to do this. Now, because we have a virtual image being produced here, we're going to have to use the image distance V as a negative value. All right, so we observe a sign convention called the real is positive. So that's real is positive and convention. And it simply is saying that any real distances, real objects, real images, their distances must be positive, given a positive value. However, if you have an image that is not real, so a virtual image, as in this case, the image distance has to be taken as negative. So this will be taken as -6. So B is -6. We have -6. and then U is positive 2. So that's negative 6 times 2 over negative 6 plus 2. Therefore, we get negative 12 divided by negative 4. That's then equal to 3. So answer is 3 centimeters. That's B. Question 40. A block is allowed to fall freely towards the ground. As it falls, its gravitational potential energy. So we know that gravitational potential energy increases as an object gets further away from the ground. But if it is falling, then it will be getting closer to the ground. And so the gravitational potential energy will be decreasing. There's no decrease here. It's not increasing, because it remains constant. It's converted to internal energy. No, it's converted to kinetic energy. So yes, the potential energy is converted into kinetic energy when an object falls. So D is the answer there. Number 41. Two smooth spheres A and B collide head-on. Which of the following statements is or are true? The momentum of A is the same after collision as it was before. This is not necessarily so. The momentum of B is the same after collision as it was before. Also not necessarily. The total momentum of A and B is the same after collision as it was before. So based on the principle or the law of conservation of linear momentum, we know that the total momentum before and after are equal, but not the momentum of the individual objects. So it's 3 only. So that's B again. Number 42. The height of liquid in a vessel is h and its density rho. If the atmospheric pressure is x and the acceleration due to gravity is g, what is the pressure on the base of the vessel? All quantities are in SI units. So we know that pressure in a liquid is equal to the density of the liquid times the gravitational field strength times the height or the depth of the liquid. But we have no atmospheric pressure to consider, so we have to add the atmospheric pressure to the pressure of the liquid. So we have x, that's x plus h times rho g Okay, so we have rho gh as the pressure for the liquid plus x, which is the atmospheric pressure. So answer should be C. Number 43. So we have a diagram, two vectors of magnitudes A and B represented by OA and OB. The two vectors act at a point O and are directly perpendicular to each other. So we have a right angle there. Which of the following pairs represent both the magnitude and direction of the resultant? So what we know is that the resultant would be from O to C, straight line from O to C, going in this direction. And based on the mathematical principle, you know that the diagonal here can be determined by finding this sum of the squares of OA and OB, and then finding the square root of that sum. So if we have A squared plus B squared, and the square root of that should give us OC, which is the which gives the magnitude, and then the direction is OC. So this is out. So is this. We have the correct magnitude given by this one, but the direction is OC instead of CO. So we have, the last option here is correct. Because even though this gives the magnitude, this doesn't give the correct direction. Number 44. A ray of white light enters a transparent glass prism. In which of the following diagrams is the dispersion of light correctly illustrated? So the glass prism will split the white light into its constituent colors, where we have red being the least deviated and violet being the most deviated. So can look at A here, seems to be correct because the splitting will take place from this point here, not at this point here. Also, the order of the colors are not correct in C nor D. So it should be red first and violet last. So we have this one is correct, A. Number 45. Which diagram best shows the path taken by a ray of light through a rectangular block? So again, we need to look for the ray bending towards the normal once it goes into the glass, but away from normal when it comes out of the glass. Also, once it is not hitting the glass at a 90-degree angle, it will show some refraction. So we don't see any refraction here. So this is out. A is also out because we would not have this exit for the light ray. Right? So the first bending is correct, but the second part is incorrect. So we have this, that one is out as well. C, we have, looks like this one is correct. Bending towards the normal when it enters the glass, away from the normal when it exits the glass. So we have this one looking to be most appropriate. In this one, the ray is bending too much away. So this would not be so likely. That one is out. So C is the answer here. Number 46. Number 46 refers to the following diagram, which shows three forces of magnitude L, M, and N, all in the same plane and applied on a ring. So they are all in the same plane, meaning they are all in the flat, if we consider on the piece of paper or the screen, they are all flat on the screen. Which of the following equations must be true, sorry, in order for the ring to remain stationary? All right, so we have L squared is equal to M squared plus N squared. So these L and M are perpendicular. So if we find the sum of the squares of L and M, then that should be equal to N square of N. Okay. So we are seeing L squared is equal to M squared plus N squared. This one will be out. N squared is equal to L squared plus M squared. So this one seems to be correct here. C says N squared is equal to L squared minus M squared. So no. And N is equal to L plus M. N would not be equal to L plus M. It's not going to be so straightforward. All right, because they are at a 90-degree angle. So the resultant of L and M would be, if we take in everything here, would be like that. So N must be equal to the resultant of L and M. And because L and M are at right angles to each other, then we know that the squares, the sum of the squares of L and M would be equal to the square of N. So that is why we have, or we would choose B for the answer here. Number 47. Two forces of 8 newtons and 10 newtons cannot give a resultant of. All right, so 8 newtons and 10 newtons, if they are acting in the same straight line and in the same direction, then they can give you a total of 18. So 18 is possible. If they are acting in the same straight line but in opposite directions, then they can give a resultant of 10 minus 8, which is 2. So 2 is possible. So anywhere between 2 and 18, any values between 2 and 18 are possible. So we find that 1 is not possible. So 1 does not occur between 2 and 18. So we have A here. All right, 48. The moment of a force may be defined as the moment of a force is the product of the perpendicular distance and the magnitude of the force. So we have, this says time here, not correct. The length of time, not correct here. Product of the force and its perpendicular distance from the turning point to the force. So this would be correct. Moment is not a ratio, so that would be out. Number 49. When a force F is applied to a spring of original length L, the new length becomes L plus X. What would be the new length of the spring if a force F divided by 2 was applied instead? So we know that from Hooke's law, extension is proportional to the force. So if we decrease the force to half its original value, then the extension would also be halved. So the length of the spring would be equal to the original length plus half of the original extension, which is original extension was X. So half of X is X over 2. So the new length would have been L plus X over 2. And that's D. Number 50, in carrying out an experiment to locate a real image when using a converging lens, the object can be placed. So we have to locate a real image using a converging lens. So we have to remember where the object must be placed in comparison to the lens, how far or at what point on the principal axis the object must be placed to get a real image. And let's look at the options we have between the focal point and the lens. So that's between F and the lens. Now, if the object is placed between F and the lens, we're going to get a virtual image. So one is out. At the focal point, if you put the object at the focal point, then you will have no image being formed really. You won't be able to locate an image. So this is out. Between the focal point and a point at twice the focal length. So you will get a real image with this one. So it's 3 only. So it's D. So you have to remember all the points where you can get a real image for the converging lens. So that would be helpful to know in order to answer this question. Number 51. The graph shows at one instant the pressure variation along a sound wave. So we have atmospheric pressure on the y-axis here and distance along the x-axis. Which point on the diagram represents a rarefaction, and what is the wavelength of the sound wave? Now, in the case of the rarefaction, particles are moving away from each other. So it means that the pressure would be below atmospheric pressure at a rarefaction point. Pressure will be below atmospheric pressure, right? So Q is below atmospheric pressure. We look for Q here. So at this point, it could be either C or D. But what is the wavelength now? Wavelength X or Y. Now the wavelength is between, for a sound wave, we could define the wavelength as the distance between two successive compressions. And we know that if Q is a rarefaction, then P must be a compression point. And so distance between the distance x would be the wavelength. Y is not the wavelength. Y is showing the amplitude, or not, well, not the amplitude, but the difference in pressure between where the particles are not disturbed and where they are disturbed, or where the pressure is atmospheric pressure, sorry, and where the pressure is a maximum. That's where the compression is. So Y would not be showing the wavelength. X is showing the wavelength. So we have Q for the rarefaction, because at the rarefaction point, the pressure would be below atmospheric pressure. And then X is showing the wavelength. So we have C here. (52). An ultrasonic tape measure is used to find the distance to a wall. It sends out an ultrasonic pulse and times how long it takes for the reflected pulse to return from the wall. The ultrasound has a frequency, a wavelength, and a speed. Which pair of values is needed to find the distance to the wall? All right, so do we need the frequency and the wavelength? So distance can be measured from velocity or speed, so v and t. So if we know v and t, then we could find d. Right? Now frequency has something to do with the time taken for one oscillation of the wavelength. But can we use the wavelength and the frequency? So if we have the wavelength and the frequency, we may only be able to find the speed, because we know that v is equal to frequency times wavelength. We know the frequency and the time taken for a pulse to return. Both of these have to do with time, so this would not give us the distance. If we know the speed and the time taken for the pulse to return, right? So we know the speed of the wave, multiply that by the time, we get a distance measurement. So C look like the most likely answer here. Wavelength and time taken. So the wavelength is a distance measurement, but multiplying the wavelength by the time would not give the distance. It would rather give another value, so meter multiplied by a second would not give us the distance. So C is the most likely answer here. Number 53. When white light is dispersed by a prism compared with blue light, or let me read that again. When white light is dispersed by a prism compared with blue light, the red light is, right. So we know that red light is refracted the least. So it means that it would have slowed down to a greater extent than the blue light, and it's refracted less. So A is our answer here. sorry. So, sorry, slow down. The red light is slowed down the most and refracted the least. Sorry about that. That should be C and not A here. All right. So if you remember for the refraction through the prism, red light, red comes first, and the last one is violet. You have blue coming somewhere before the violet. So the blue light is refracted more than the red light. So the speed of the red light would have been reduced to a greater extent than the blue light. So red light slowed down more, also refracted less. '54, a fixed mass of gas at constant temperature is compressed to reduce its volume. How do the molecules of gas now strike the walls of the container? So if the temperature is kept constant, but the volume is reduced. Because the volume is reduced, the gas molecules will travel shorter distance. So they'll strike the walls more often. But now the temperature is constant, so they are going to be moving at the same speed. All right, they have the same velocity, but they just are traveling a shorter distance. So this means that you have more collisions, but with the same velocity. Number 55, which diagram correctly represents water waves traveling from deep to shallow water? So one thing you have to know for this one is that water waves will travel faster in deep water than in shallow water. So we should have the wavelength being shorter in the shallow water. Okay, so we look for such a diagram. Now the speed of the waves will decrease going into the shallow water. So we'll have the bending, the refraction of the rays, of the waves, sorry, will be towards the normal. If we have a straight line, let's try to put in a straight line here to represent the normal. It's roughly here. Now we'll eliminate B and D, because if the waves are traveling faster in deep water, it means that the wavelength should be the distance between the wavefronts would be greater. But we don't have that here and here. So we would have eliminated B and D, leaving A and C. But because the waves slow down in the shallow water, then we'll have the waves bending towards the normal. So A they're going towards normal more. In here, they are going away. In C, they are going away from normal. So we'll choose A here. Number 56, which characteristics describe an image formed by a plane mirror? Real and inverted. In a mirror, the object, the image is not real, it's virtual. And it's inverted laterally. All right, virtual and upright. Real, no, it's not real. So virtual and smaller, it's not smaller. So virtual and upright. It's not inverted, except laterally. In this case, they didn't say laterally inverted, so we have no matching answers except in B. 57, the range of frequencies detectable by the human ear is normal human ear. So this is something that you would need to recall. 20 hertz to 20,000 hertz. 20 hertz, 20 kilohertz. Kilo is 1,000. So the answer is B here. 58. A man is short-sighted, which ray diagram shows what happens when he looks at a distant object. So in a short-sighted person, could be that their eyeball is too long, or their cornea is too powerful. So when they look at a distant object, the rays are bent to meet in front of the retina. Right? So there is no bending in A. Bending in B results in the rays meeting on the retina. So this is not for a person with short-sighted. In C, for the rays meet in front of the retina. So this is the likely answer. In D, meet behind the retina. Not this one. Because if the eyeball is too long, the rays would meet in front of the retina, not behind it. So we have C for this one. 59, the penultimate one. Which color, red or blue, has a higher frequency and which has a longer wavelength? So, electromagnetic spectrum, we know that red light has a longer wavelength. Right? Now, what you can do is to look at the equation V is equal to F lambda and the speed of these waves in a particular medium would be the same. Right? So there is a inverse relationship between F and lambda. So if red light has a longer wavelength, it means that it must have a shorter frequency than the blue light. Okay. So higher frequency would be the red, would be the blue light, sorry. And the longer wavelength would be the red. So we have blue for higher and longer is red. So B here. All right, the last one, number 60. Waveforms that are shown on a cathode ray oscilloscope for a flute and a guitar playing the same note. oscilloscope settings are the same for both waveforms. What is the difference between the two sounds? Now, we know that the different instruments play the same note with a different quality because of the mixture of the fundamental frequency with other frequencies. So we see that if fundamental frequency is the same, if we should look at the distance between, this will be the time gap on the x-axis. It's not shown, but that is what it is. So the time here between these two peaks, the same here. So there is no difference in frequency, no difference in amplitude or wavelength. So it's the quality. Different instruments play different quality. If they are playing the same note, they will sound a bit different because of the quality. All right, so that's it. All the best in your exams.